Hello students, in this video I am going to explain ideal solutions and non-ideal solutions and azeotropes, different types of azeotropes. Please subscribe to my channel, like, share and comment my videos.
In a binary solution of two volatile compounds, binary solution of two volatile components, A and B. Now, partial vapor pressure of each component, partial vapor pressure of each component. How do we get? Partial vapor pressure of each component is given by PA is proportional to XB, where PA is the partial vapor. PA is proportional to XA, where PA is the partial vapor pressure of the component A and XA is the partial vapor pressure of component A. Implies PA is equal to P0A into XA, whereas P0A is the vapor pressure of a pure component. So here P0A is the vapor pressure of a pure component A. PA is the vapor pressure of a component A in the mixture, and XA is the mole fraction of component A. So PA equal to P0A into XA. Similarly, PB is equal to P0B into XB. Now, total vapor pressure of the mixture. How do we get the total vapor pressure of the mixture? If we add the partial vapor pressure of component A and partial vapor pressure of component B, then we get the total vapor pressure of the mixture. Therefore, P total equal to P0A XA plus P0B XB. So this is the total pressure. Now, so here we know that XA plus XB is equal to 1. Sum of the mole fractions of all the components is equal to 1. Therefore, XA is equal to 1 minus XB. So let us substitute this here. So P total equal to P0A into 1 minus XB plus P0B XB. So this is nothing but P0A minus P0A XB plus P0B XB. Therefore, this is equal to P0A minus XB into P0A plus P0B. So, from this equation, the total vapor pressure of the solution, the total vapor pressure over the solution can be related with the mole fraction of any one component. So, mole fraction of component B we considered. Therefore, the total vapor pressure over the solution can be related with the mole fraction of any one component. Here we took the component B. Now if we take a graph, say this is the graph. Here this is the vapor pressure, and of course this is also vapor pressure. Here this is the mole fraction. Here XA equal to 1, XB equal to 0. Here XA equal to 0, XB equal to 1. So if we take the graph taking the mole fraction of B, the mole fraction comes in this manner, like this. So this is the component B, and of course this is the component A. This is A, this is B. So if you start from here, the mole fraction of component B starts from 0 and reaches 1 here. That means here this is the vapor pressure of pure component B. Similarly, this is the vapor pressure of pure component A. Now if we join this line, these 2 points, this is the vapor pressure of mixture, vapor pressure of mixture A plus B. So this line shows the vapor pressure of a mixture A plus B, right? So what is the first point here? What we concluded? The total vapor pressure over the solution is related with the mole fraction of any one component, and the second one is the total vapor pressure of the solution varies linearly. Linearly means straight line. Varies linearly with the second component. So these are the two conclusions we have drawn from this equation. So the third point is depending on the vapor pressure of pure components, the total vapor pressure, that is P total will be less or more. So these are the conclusions drawn from this equation. So what is Raoults law? Raoults law states that So Raoults law states that the partial vapor pressure of any component in a binary solution of two volatile liquids is directly proportional to the mole fraction. Therefore, partial vapor pressure PA is directly proportional to X. Implies PA is equal to P0A. P0A is the proportionality constant and P0A is the vapor pressure of the pure component A into XA. Now, if one of the components is since we took here component A, so if the one of the components that is A is gas, if it becomes gas, then what happens? Partial pressure of the gas A over the liquid B is proportional to XA. This implies PA is equal to KH into X. KH into X or XA. So what happens? So there is a Raoults law is an extension of Henry's law. Raoults law is the extension of Henry's law, right? So here what we discussed this is the binary solution of two volatile liquids. Partial vapor pressure of any component is given by PA equal to P0 into XA. If PA becomes gas, then what happens? Partial pressure of the gas over the liquid is proportional to the mole fraction of the gas dissolved in the liquid. Therefore, PA is proportional to XA, PA is equal to KH into XA. Therefore, here KH equal to P0A. KH is the Henry's law constant, whereas P0A is the vapor pressure of a pure liquid. So this is the relation between Henry's law and Raoults law. Now, if the solution has a non-volatile solid solute, non-volatile solid solute. Non-volatile solid solute. Then what happens if we draw the graph for a non-volatile solution, a solution having a non-volatile solute, then if we draw the graph between vapor pressure and mole fraction, the graph between vapor pressure and mole fraction will come as a straight line. So here x equal to 0, that is mole fraction of the solvent. Here the mole fraction of the x equal to 1. Right, that means here at this point there is no solute in the solvent. Right, so solutions having a graph in this manner, they are referred as ideal solutions. So ideal solution. So what is meant by ideal solution? Ideal solutions are those which obey Raoults law at all concentrations. Ideal solutions are those which obey Raoults law at all concentrations. So ideal solutions are those which obey Raoults law at all concentrations. So during the formation of an ideal solution, delta H mix, that means enthalpy change during mixing of the two components, delta H mix equal to 0. Similarly, delta V mix, that means volume of both the components, sum of the volumes of both the components during the mixing is equal to 0. That means there is no increase or decrease of enthalpy. Similarly, there will be no increase or decrease of volume. So these are the two conditions during the formation of an ideal solution. Why it is so? The delta H mix and delta V mix, why they become 0? So during the formation of ideal solution, inter-attractive forces, intermolecular forces or inter-attractive forces between AA and BB. A is the one component and B is the one component. So inter-attractive forces or intermolecular forces between component A and component B is exactly equal to intermolecular forces between between A and B. So these are the old forces, these are the new forces. So the sum of the old forces become equal to the sum of the new forces generated. So because of both the forces before mixing and after mixing are same, therefore delta H mix and delta V mix is 0. That is during the formation of the ideal solutions. But strictly speaking, any solution is not perfectly ideal solution. Right. So this ideal solutions is referred to the binary solutions of two liquid components. So ideal solution is referred to binary solutions of two liquid components. Right. So as we discussed just now, that is any solution is not perfectly ideal solution, but few solutions they behave almost like ideal solutions. Therefore, examples of ideal solutions. Here, as I am mentioning, ideal solution means they behave nearly to the ideal nature or ideal behavior. For example, benzene and toluene, C6H6 and C6H5CH3. This is an example of an ideal solution. Similarly, N-hexane and N-heptane. N-heptane. N-hexane and N-heptane also behaves like ideal solution. Similarly, C2H5Cl and C2H5Br, chloroethane and bromoethane act as behave like ideal solutions. So ideal solutions means the ideal solutions are those which obey Raoults law perfectly all right at all concentrations. That is the ideal solution, right? So binary solutions of two liquid components. So binary solutions of two liquid components, just now we discussed that there are ideal solutions. So this is ideal solutions. Ideal solutions means obey Raoults law perfectly at all concentrations. If it is not ideal solution, then what is this? Non-ideal solution. Non-ideal solutions means which do not obey Raoults law. So do not obey Raoults law. So here delta H mix is equal to 0, delta V mix is equal to 0. Here delta H mix is not equal to 0. Not equal to 0 means it may be less or it may be more. Now let us discuss those conditions after 1 minute. So delta V mix is not equal to 0. Now non-ideal solutions are of two types. Non-ideal solutions are of two types. Non-ideal solutions showing positive deviation, and non-ideal solutions showing negative deviation. The positive deviation means, see, in intermolecular forces between AA and BB are greater than intermolecular forces between A and B. Because of this, component A vaporizes quickly and component B vaporizes quickly. That means during the formation of this solution, AA individual molecules and BB individual molecules vaporize at faster rate. Therefore, vapor pressure is more than expected as per Raoults law. Therefore, this is a positive deviation. In case of negative deviation, it is on opposite. That is, the intermolecular forces between AA molecules and BB molecules is less than that of intermolecular forces between A and B. Because of this, the vaporization process of individual A component and individual B component is lesser. Therefore, it shows the negative deviation. That means vapor pressure becomes less as compared according to the Raoults law. Whereas here the vapor pressure is more, vapor pressure of the mixture is more as per the Raoults law. That is positive deviation and negative deviation. Now let us discuss, let us try to understand this in the form of a graph. So this is the graph. This is mole fraction. This is XA is equal to 0, XB is equal to 1. Here XA is equal to 1, XB is equal to 0. So this is vapor pressure. So XA equal to 0 means it increases from 0 and of course reaches here in this manner. Whereas here XB equal to 1, that means this is the XB equal to 1 and of course it starts XB equal to 0 here. So this is the This is A, this is B, this is vapor pressure of A plus B. Now positive deviation means the curve comes in this manner, like this. That means the vapor pressure of each component is more than expected by Raoults law. So this is for component B, it is in this manner. For mixture, the vapor pressure is more than expected as per Raoults law. This is a positive deviation. Positive deviation. Positive deviation. Positive deviation means the vapor pressure, the actual vapor pressure is more than expected as per Raoults law. As per Raoults law. So this is positive deviation. Coming to the next one, this is the graph for negative deviation. Negative deviation. So here XA equal to 0, XB equal to 1. Here XA equal to 1, XB equal to 0. This is a mole fraction. Mole fraction. So this is as per Raoults law, the graph should come in this manner. Graph should come in this manner. This is vapor pressure. This is vapor pressure. So this is a component A, component B, and of course this is a vapor pressure of mixture of both the components A plus B. So as this negative deviation, the actual vapor pressure of each component is less as expected per Raoults law. So it comes in this manner, like this. So here the vapor pressure of the mixture comes in this manner. Therefore the dotted line shows the actual vapor pressure of each component and vapor pressure of the mixtures. So this is referred as negative deviation. Negative deviation. So here the actual vapor pressure of the mixture is less than as expected, as per Raoults law. So these are the positive deviations and negative deviations. Now what are the examples for positive deviations and negative deviations? Let us see some examples. During the formation of non-ideal solution showing a positive deviation, delta H mix is greater than 0. Similarly, delta V mix is greater than 0. In the same manner, for solutions which show negative deviation, delta H mix is less than 0. Delta V mix is less than 0. Right? Delta H mix and delta V mix both are less than 0, whereas in this case delta H mix and delta V mix both are more than 0. More than 0 means positive. Here negative. Right. Now let us see some examples of these different types of non-ideal solutions showing positive and negative deviations. So examples: CH3 taken twice CO, acetone plus CS2, acetone and carbon disulfide, acetone CH3CO plus C2H5OH, acetone and ethyl alcohol, and acetone plus benzene C6H6, carbon tetrachloride and chloroform, CH3CHO, acetaldehyde and carbon disulfide, water and alcohol, water and methanol CH3OH, chloroform and ethyl alcohol, chloroform and ethyl alcohol. So all these are the examples of non-ideal solutions showing positive deviation. Now let us see Examples of non-ideal solutions showing negative deviation. Negative deviation. Negative deviation. Acetic acid plus pyridine C5H5N. This is pyridine. Acetic acid and pyridine. Chloroform and acetone. CH3 taken twice CO plus chloroform CHCl3. Chloroform and acetone. CHCl3 and C6H6. Chloroform and benzene. Chloroform CHCl3 plus C2H5 twice O. Diethyl ether. Chloroform and diethyl ether and water and nitric acid. So these are the examples of non-ideal solutions showing negative deviation, and of course these are the examples of non-ideal solutions showing positive deviation. So different. What is the reason for this? The reason is, in this case, A and BB attractions are more than AB interactions. Therefore, the pure component vaporizes quickly. Therefore, vapor pressure of the mixture is more. In this case, A and BB attractions are lesser than the AB attractions. Therefore, the vaporization of a pure components becomes less. Therefore, they show negative deviation, that is, the vapor pressure of the pure mixture is less than as expected by Raoults law. So that is non-ideal solutions. Now let us see the constant boiling mixtures. Constant boiling mixtures. Constant boiling mixtures are also referred as azeotropes. Azeotropes. What is meant by constant boiling mixture or azeotrope? A mixture of two liquids. A mixture of two liquids boil at a constant temperature. Constant temperature, as if it is a pure liquid. A mixture of two liquids boil at a constant temperature as if it is a pure liquid is known as constant boiling mixture. So a mixture of two liquids boil at constant temperature as if it is a pure liquid is known as constant boiling mixture. In a constant boiling mixture, the composition of two liquids in the liquid state and vapor state are same. Liquid state and vapor state is same. That means the composition of both the liquids in liquid state as well as vapor state is same. That is constant boiling mixture, or is also called as azeotropes. Again, azeotropes are of two types: minimum boiling azeotrope, maximum boiling azeotrope. Now let us discuss azeotropes. Azeotropes are those binary solutions of two liquid components whose composition in liquid state, liquid phase as well as in vapor phase is same and boil at the constant temperature. That is azeotrope. Azeotropes are of two types. Azeotropes are of two types. That is minimum boiling azeotropes. Minimum boiling azeotropes. Minimum boiling azeotropes means those liquid mixtures which show large positive deviation from the Raoults law. So mixtures are solutions which show positive deviation from Raoults law. Raoults law become minimum boiling azeotropes. This minimum boiling azeotropes, they show their boiling point is least, less than the least. So here, so in case of minimum boiling azeotropes, vapor pressure is highest, and boiling point is least. Vapor pressure is highest and boiling point is least. Let us see example. Water plus ethyl alcohol. Water and ethyl alcohol. Water boils at 373 Kelvin, whereas ethyl alcohol boils at 351.3 Kelvin. Therefore, the mixture boils at 351.1 Kelvin. That is, the boiling point is less than the least boiling point of the pure component in the mixture. So these are minimum boiling azeotropes, are those solutions which show positive deviation from Raoults law. They have a highest vapor pressure than expected as per Raoults law, and of course boiling point is least. On the other hand, maximum boiling azeotropes, as you understood the minimum boiling azeotropes, you can guess the maximum boiling azeotropes. Maximum boiling azeotropes are those solutions which show negative deviation from Raoults law. They have least vapor pressure as expected by Raoults law, and of course boiling point is highest. Example, water plus nitric acid HNO3. Water and HNO3. Water boiling point is 373 and boiling point of nitric acid is 359 K. Therefore, the mixture boils at 393 Kelvin. That is, the boiling point of the mixture is greater than the greatest boiling point. Out of these two components, water has the greatest boiling point. The boiling point of the mixture is greater than the greatest boiling point. So this is maximum boiling azeotropes.